and welcome to Lecture 11 supplement on honesty that is intended for graduate students. So this is meant to supplement the honesty lecture that was delivered earlier. That is called Lecture 11 in Engineering Ethics. So the first thing I like to do is start with a cartoon. I love these Calvin and Hobbes cartoons, so let's just read it. Calvin says, I don't believe in ethics anymore. As far as I'm concerned, the ends justify the means. Get what you can while the getting's good. That's what I say. Might makes right. Winners write the history books. It's a dog-eat-dog world, so I'll do whatever I have to and let others argue about whether it's right or not. So Hobbes pushes him. Why'd you do that? You were in my way. Now you're not. The ends justify the means. I didn't mean for everyone, you dolt, just me. Ah. So, connected to this issue of morality is moral relativity. So, the idea is you approach c, speed of light, rationalization goes to infinity. So related to moral relativism, it states that ethics becomes subjective only when you approach the speed of light. That is, it's okay to be self-serving, steal, and murder as long as you're going really, really fast. Anyway, enough cartoons. So let's talk about research integrity. So research in engineering occurs in universities, government labs, and corporations, all three. Each play an important and connected role, although research in corporations, the body of research in corporations has gone down over the last 30 years. So, truthfulness takes on a heightened importance in research because research aims at discovering and promulgating the truth. As we discussed in Lecture 11, truthfulness in engineering is crucial in honesty in reporting specifications, for instance. Truthfulness has a similar heightened importance in research. In fact, you can have a lack of truthfulness by simply doing sloppy research. In a certain way, it's fundamentally dishonest. So what does it mean to be truthful in research? It means honesty in conducting and reporting experiments. In other words, you don't cook data, you conduct them in a fair way to try to uncover principles. You don't steal other people's results. You don't misuse research funds. You're a good steward of funds. So, National Science Foundation defines misconduct in science and engineering as, well, it could be a number of things. They say it's fabrication, when you make up results, falsification, when you change results or misrepresent results, plagiarism, when you steal other people's ideas or work and present it as your own. And this is in some ways more of a problem these days because of the simple ability in electronic word processing to copy and paste. For instance, to copy and paste out of a web browser when you're searching the internet into a document. Or other serious deviation from accepted practices in proposing, carrying out, or reporting results from activities funded by NSF, or retaliation of any kind against a person who reported or provided information about the suspected or alleged misconduct and who has not acted in bad faith. So, what typically people call fraud is the gross versions of the above. Years ago, in fact, there was an establishment of some of the problems in the ethics and fraud and research by Babbage, one of the original early scientists. He said forging something was a deception intended to establish one's reputation. In other words, stealing a document, putting your name on it, that is forging it, acting as though it's yours when it's not. Hoaxing is a type of deception that's intended to last for only a while and then to be uncovered or disclosed, typically to ridicule those who are taken in by it. This also occurs on the internet as a problem. Trimming is to selectively omit bits of outlying data. So you get some data that are far from the mean, for instance, and you throw them away so that your results look more consistent. That is, you trim the data. Cooking. This term is still used today. The idea of cooking data is you selectively report results. That is, only the good cases. You falsify data or massage data in the direction that supports the result that you want. These days, it's become it's just as easy today, maybe even easier, to do cooking of data. So you can get experiments out of laboratory, and even if you have a data gathering system that dumps the data to a figure in an EPS file, you can edit the EPS file directly and change data point positions on a plot. You can edit just about anything. So it becomes quite a problem, including images, of course. You can edit using Photoshop images. There's all kinds of possibilities for deception in research. So let's talk about bias and self-deception. So if there's a rush to report results before peer review, such as in the cold fusion case, or this typically results in self-deception. Self-deception meaning you sort of deceive yourself into thinking that something is true, and it's best to avoid that, of course. And one good way to do it is to ask others to critically review your work, for instance, via the peer review process. There's also conflicts of interest that cause bias, like if you own large shares of in a stock in a company that you're doing research for, or if you have a promise of more research funding if the results favor the products of a company, or they fund research to show a product is better than another when it's not. In other words, you're asked by a company, show our product's the best, and you find out, well, it's not, and then you report instead that it is the best. Next, in terms of protecting research subjects, this is a tricky issue. It arises in many areas of engineering, especially in biomedical engineering, but it also arises in sometimes in mechanical engineering or electrical engineering, associated with automotive research, for instance. So experiments on humans are only permissible after obtaining a voluntary consent of the human subjects. They have to have all the information on the risks, the possible benefits. There can't be coercion to be a subject or to do something. So in the United States, there's human subjects have to receive the following. They have to receive information on the purpose of the experiment and procedures to be used, foreseeable risks and discomforts, foreseeable benefits, appropriate alternatives, if any, the extent of confidentiality of the test results, the availability of medical treatment for any injury received during the experiment, and compensation for any disability, whom to contact in case of questions, and assurance that participation is voluntary and that neither refusal to participate nor later withdrawal from the study will result in loss of benefits to which the person is otherwise entitled, such as future care at the same facility. The way these issues such as this are managed in a university is to have an institutional review board, or IRB. They seek to protect human subjects. They review research protocols of all experiments involving humans, and they have detailed guidelines that have to be met before an experiment can be conducted. Human subjects are also used in product testing in industry. If you, however, do not get federal funds for that, you're not subject to the regulations, but you're bound by standard engineering ethics and many of the issues that are on the previous slide. So there's also experiments on animals, typically to benefit humans. And the question becomes what species to use. Can we use mammals? Does intelligence level of the animal matter? For instance, using bacteria, most people don't have trouble with that, but many people have trouble with using primates in research, especially if it hurts the animal. Or what about animals with complex social systems? The suffering of one animal sort of adversely affects others in the group, as in many primates. What about human pets, dogs and cats, for instance? In university research, there's regulatory boards for vertebrates, and for some animal testing, there can be some federal standards too. So I wanted to show you another cartoon on honesty. I love this one on the bottom with Bart saying, "I'll not plagiarize others' work." And then this one, if you cut and paste it from the web, he'll say you plagiarized. I didn't cut and paste it. I printed it and then typed it in. Is that plagiarism? I mean, I typed it. Of course, it's plagiarism. So giving and claiming credit, and the problem of avoiding plagiarism. This is very important. This is intentionally or negligently submitting others' work as one's own. The failure to give credit. So here's a case from the National Society of Professional Engineers Board of Ethical Review. A city hires an engineer to design a bridge, and the engineer in turn subcontracts some key design work to a second engineer. Months after the bridge is completed, the first engineer submits the design to a national design competition where it wins an award, but he fails to credit the work of the second engineer. Obviously, that's unethical. Okay? Failure to give credit where credit's due. Just like in plagiarism, it's failure to give credit where credit is due. Citations. So you have to give credit where credit's due, but you have to figure out where it's due, and this is complicated in research. You have to clarify in your research papers, for instance, what you've contributed and what you have not. You have to essentially stake your claim and say, this, for instance, was these were the contributions of the previous paper. Here we're doing this, which is different and important, and a direct extension of that work, for instance. You have to be very specific then about what's in others' papers, how it relates, and really you have to highlight the most similar work, and that's difficult to do because there's a lot of work going on there in research. In research, who does what first matters. It matters a lot. You might say, why? Well, to get a PhD, you have to do something that's completely novel, completely new. Therefore, you have to do something of significance first. And you have to be able to argue that in terms of the existing literature in a convincing manner. Here's interesting. So, see, it's a universal rule. They fall at the same rate. Great. Is there a universal rule for who will be the first author in the paper reporting it? Well, no. Picking the order of authors and other authorship issues is really quite difficult. So, there's other issues that are problematic too besides author ordering, such as misrepresenting credentials. If you say you have a degree that you do not have, you only did part of the coursework. There's misleading of listing of authorship. The order of the authors in an engineering work is generally research papers, anything, is the greatest contribution. Your greatest contributor is first, and the least contributor is the last. Sometimes, though, there's problematic things that are done, such as omitting a co-author who helped the author, or misordering those names, putting, for instance, a senior person first who hardly did much work on the project just because he or she is a single person. Sometimes people have motivation to add a person who has nothing to do with the paper, just to try to help that person out get more papers, publications, and credit. And that's certainly not ethical. It's very important to also use an acknowledgement section. Sometimes if someone is not really, it's not really justified to make them a co-author because they didn't contribute anything or that much. You put them in an acknowledgement section and say what they did offer. There's also rules for journals and conferences with respect to how all this is done. And there's also rules with respect to reporting any misconduct that you see. Let's talk about reviewing a paper, which many graduate students are asked to do. And after you graduate are, you're often asked to do it if you're a graduate student. Usually at a conference, there's 2 to 3 people that are reviewing a paper. Journals, 3 to 4 people typically. And there are different standards. It's sort of easier to get a conference paper, a lot harder to get a journal paper, generally speaking, although some conferences review very tough. It is an opportunity to learn. You find out, what are really good papers and what are bad papers, so you try to improve your own writing. And it's important to really try to fairly evaluate the work, especially with respect to the literature. And if you don't know the literature in the area, you just say, well, this looks really good, but I don't know what the literature is. I don't know how much of a contribution is. So just be fully honest in your review. There's nothing wrong with saying something like that. You even may conduct a simulation or check a proof of what someone is saying. So it's important, the following. The contents of the paper are confidential. That means you can't share the contents of the paper. That means you can't use the results yourself. If you talk to the advisor and get help in reviewing, then you and that person should be listed as a reviewer, and you can't use their results. Next, in consulting engineering, deceptive advertising is sometimes found, for instance, outright lies or half-truths, saying that part of big projects, you may say that you're part of a big project where you only had a minor role in. You might exaggerate the quality of past products. You might use false innuendos, suggestions, or implication. You might have obfuscation created by ambiguity, vagueness, or incoherence. There's also issues in competitive bidding. Some people say you're not allowed to do competitive bidding, since then you would only rely on reputation and proven qualification and not the technical quality of a design, for instance. There's also this issue of contingency fees. So the NSP Code of Ethics says the engineer shall not request, propose, or accept a commission on a contingent basis under circumstances in which the judgment may be compromised. So a contingency fee depends on a special condition beyond the performance of satisfactory work. For example, that you will save the client money. This may lead to inferior design in the use of low-cost materials. Next, when it comes to safety and client needs, consulting engineers have the option to accept design-only projects. But there's problems with this. There's no follow-through with the client to monitor how the project is going, and there's no monitoring of safety issues that unexpectedly arise. You just create a design, you hand it over to somebody else, there can be problems. So you have to be concerned about the ethics of essentially social experimentation, for instance. Next, I have a few other cartoons. The one on the left, it says, during the course of the trial, both sides had ample opportunity to call on their expert witnesses, and they're all chickens. I thought that was kind of funny. So with respect to this expert witness issue, people that have graduate degrees in engineering often are asked to be expert witnesses or expert advisors. So expert witnesses in the courts, you can be hired by the plaintiff or the defense. You give testimony on defective products, personal injury, property damage, traffic accidents, or airplane crashes. It's okay for engineers to follow how lawyers do and have an adversarial role on either side. That is only to argue for one side, because both sides can hire the experts. This is not actually okay to be like a lawyer. Your primary objective is in responsibility is to be objective, technically objective, to state what's technically true and what is not true. If it doesn't entirely fit into what the lawyer wants you to say, so be it. You have to stand on your own 2 feet and make expert testimony that is unbiased. The role of expert witnesses is to identify the truth about the causes of the accidents, not to directly serve the attorney's clients. Attorneys hire and pay engineers for their services in impartially investigating the truth. Engineers should not become the so-called hired guns who engage in outright lies and distortions according to who pays their consulting fee. So some of the abuses are hired guns, financial biases. If you're being paid by one side, this can exert some bias. You should never get hired based on a contingency. You're being paid only if you win the case. There can be ego biases. Adversarial situations evoke competitive attitudes that can influence judgment. And there's sympathy biases, and where you let the judgment be influenced by the victims. You have to avoid such biases and try to stay technically objective. Next, expert advisors in planning and policy making. For example, engineers hired by pro-nuclear corporations or anti-nuclear groups invariably feel pressure to accent one side of the case, and that can be unfair. The assumptions made that on these kind of cases can matter, and they can bias solutions. If you study only one part of the problem, that can create a biased solution. It can be very difficult to give good expert advice. So, it's another hired guns problem. Hire an expert advisor to try to show their side of a case. And these engineers certainly should not do that. They should be value neutral analysts. They should be completely impartial, avoid a taint of bias, favoritism, and advocacy, and they should be value guided advocates. They can adopt partisan views in controversial issues, but remain honest and independent in their professional judgment. They make their responsibility to the public paramount, and they can make a stand, no matter who that's for. So some sources for this that I wanted to highlight is this Carolyn Whitbeck, Ethics in Engineering Practice and Research in 2011. And then I also got some ideas for some of the earlier parts of these slides from Professor Ness Schroff in this talk that he puts at his website. So here's your view check question. So you work with your advisor, a graduate advisor, for 2 years. You write a paper without his or her explicit help. Should you put his or her name on it? Thank you.